Hello, welcome to the latest episode of Stars, Cells, and God, where we look at the latest scientific evidences and see what they have to say about the truth of the Christian faith. Looking forward to our time today talking with Dr. Mike Strauss. Would encourage you to go to reasons.org if you want more information. Follow us on YouTube, click the like button, subscribe, follow us on social media, go to RTB_official. And so just looking forward to our time today. Going to bring Dr. Mike Strauss in. He's a particle physicist, works at the University of Oklahoma. Mike, why don't you tell us a little bit about the research you do and just give us a little bit of background on who you are.
Yeah, I'm currently, as you said, at the University of Oklahoma, but I do my research at CERN laboratory, which is probably the world's most premier particle physics laboratory. It's located on the border of Switzerland and France in Geneva, Switzerland. I work on a collider called the Large Hadron Collider, or LHC, and that collider was the one that discovered the Higgs boson back in 2012.
Well, that's kind of cool because I know one of the discoveries we're talking about is, the mass of the Higgs boson, what we can find out about it. So this is not just some paper you've read. This is something you've been actively involved in.
Yeah, there were 7,000 authors on the two papers that discovered the Higgs, and my name was one of the 7,000. But since then, I've been doing more research trying to measure the properties of the Higgs boson precisely, which we'll talk about, and actually looking for other Higgs-like particles that are expected by many models that we call beyond the standard model, models that go beyond what we know about the fundamental particles of the universe.
So why don't you, let's kind of dig right in. I know we're looking at the fruitlessness of the Higgs searches. And so why don't you tell us what about the Higgs searches is interesting in the fact that they're fruitless, and what does that tell us?
Yeah, so let's step back a little bit. The goal of course, pure science, particularly a science as cutting edge as particle physics, is to learn things about the universe that we don't know. The things that we already do know, we kind of ignore in some sense. In fact, we collide protons together 40 million times a second at the Large Hadron Collider, and we can only keep about 2,000 per second on tape to analyze later. And a big process is saying, well, which of these 40 million collisions per second, did I say million or thousand, but which of these 40 million collisions per second might be something new? And those are the things we write to tape to eventually analyze. And so that's
an amazing number. You go from 40 million down to 2,000. I mean, it's like
1 to 2,000.
The bulk of the thousand plus factor reduction we're just effectively throwing away, if you will.
Yeah, and if you don't write a good trigger, you don't get it. To give you some scale, a Higgs particle is produced about 1 every 10 billion collisions. And
wow.
So, that's the one we care about out of those 10 billion.
So if you're doing that takes, 1 every 10 billion, you're at a few, 40 million a second, roughly one a day, you might produce a Higgs, something on that order.
Yeah, we've probably produced a few thousand of them over the course of 6 years or something that we've run.
Okay. That's not a lot. It just seems like there's more, but that's a pretty intense experiment for a few events.
Well, and of course, we're looking for things that are even more rare. There's a great plot that physicists make of the processes we've actually seen and how rare they are. And they're on a log plot, and they cover, many orders of magnitude of rarity. And the things we are now seeing are even more rare than that. And that's the point, is we're always looking for new things, not things we already know. There are two ways we look for new things. One is to look directly for a new particle. Is this, for instance, a particle that's never been discovered? And we're doing that with the Higgs boson. We're looking for new types of Higgs bosons in which some theories predict there should be some. But another way we look for things we don't know is we make very precise measurements that are based on like a particle we do know. What's the mass of the Higgs? How does it interact with other particles? And then we compare that to very precise theoretical calculations. And if the measurement is off from the theoretical calculation, we've either discovered something new, or we at least have to refine the theory. Mm-hmm. And so I'm actually involved with both. I'm making measurements of the Higgs boson that was discovered in 2012 and precisely measuring its properties. And I'm also doing experiments that are looking for new Higgs bosons that are yet to be discovered.
So I question about the search for, or studying the Higgs mass. One of the things that I recall being said was that a challenge in looking for the Higgs in the first place is that we weren't able to calculate its mass or know what it was. So how can we at this point in time go and say, well, we've made a very precise calculation of the mass and can compare it to our experimental value? How can we do that if we couldn't calculate what it was supposed to be in the first place?
Yeah, that's a great question. The major measurements we're making of the Higgs are not necessarily its mass. Certainly there are correlations with mass and other properties, and we care about those. But the more important measurements are the Higgs is supposed to give mass to other particles. So there should be a direct relationship between how often the Higgs interacts with other particles and what those other particles' mass is. And so we've made that plot. If it's more massive, it should interact more with the Higgs, and it should be basically a linear relationship. And so it's not necessarily the mass of the Higgs, which is the primary measurements we're making to understand its properties, but other properties of that particle.
Okay, so it's a bigger search of just looking at how can you characterize all the various properties of the Higgs, and that then you can compare with, does that match what we can do from these detailed calculations of other parameters or other quantities that we know?
Right, and it's exactly, and there's many of those. What we call its coupling, how it interacts with particles, its spin, because the Higgs is supposedly a spin zero particle. And we've measured that. It is a spin zero particle, and many properties. And again, there are correlations indirectly with the mass and what we would expect about other aspects of particle physics, and we can look at those as well.
So you said, at least part of the interest in doing these types of experiments is seeing do the calculations for what we expect align with the measurements of what we measure, and then also looking for new particles, other Higgs particles, those sorts of things. So have we found anything in there of interest that says, hey, there's something more?
Frustratingly, no. So since the Higgs was discovered in 2012, there's been a few minor things. We've maybe discovered a particle made of 5 quarks, which was not unexpected, but not totally predicted. But nothing major has been discovered. And this has actually been quite challenging and even frustrating for particle physicists. We had expected that after running the Large Hadron Collider for 10 or 12 years, that we would have seen something new that was outside of our model, what we call the standard model, and so far we haven't. And so we are continuing to improve the detector and improve the accelerator, and hoping that nature has something. We know there's more than the standard model from cosmological measurements, from dark energy and dark matter, but we don't know what those are at the subatomic particle level. And that's what particle physics is looking for.
So the frustrating part is, there needs to be something else out there, and yet you didn't find anything. So it's not like, I just remember, I forget the exact year, but when the WMAP results were announced, I happened to be working at UCLA, and that there was a fellow over there who's one of the lead investigators on that. And I remember the tenor of the room was, when he came in, there was just this excitement, and he came in and basically said, well, we've made all the measurements, did all the calculations, and we confirmed that our assessment of the universe is correct. And there was a relief and a disappointment at the same time. The relief was, okay, we got it right. The disappointment is, well, this doesn't tell us anything new, and we know there's more to do there. And so it sounds kind of similar to what's going on here with these Higgs searches.
Very similar. And in fact, it's not just the Higgs searches, it's all the data coming out of the Large Hadron Collider. The analogy I often give is that we had a jigsaw puzzle called the standard model, and we knew what the expectation for all the pieces were, and the Higgs boson was the last piece. And we know there's another puzzle out there because there are things we're missing, like dark energy and dark matter. But not only have we not found the first piece, we don't even know what the picture on the cover of the box looks like. And so, the person that finds that first piece will win a Nobel Prize. It will open up a whole new realm of things to investigate.
So what's the connection between these fruitless Higgs searches and Christianity or God? I mean, it's kind of like, well, we don't, I mean, yeah, you could in a wrong way say, well, we don't have any explanation, therefore God's doing it, which is a dumb way to argue. And, we could don't need to delve into there. But so what is the connection? Why is this important as an apologetic?
Well, I think there's a few things. First of all, the fact that I write a mathematical theory that I expect will somehow describe the universe. That looks a lot like design. Engineers write mathematical theories to predict how an airplane wing will handle its stresses, or a building will stand up in crosswinds or whatever. And even Peter Higgs in 1963, writing a mathematical theory that said, we predict that there should be a particle out there, is because the universe is ordered and described by mathematics. We spent arguably $20 billion and 40, 50 years looking for the Higgs boson because the mathematics written down said it should be there.
Mm-hmm.
In any other field other than the natural sciences, you would say there must be a designer out there. And the fact that, when I find a discrepancy between my data and the mathematical theory, the immediate conclusion is either the theory is wrong, in other words, we don't yet understand the universe, or I've discovered something new. Well, why is it that I can even understand the universe? That Einstein's famous, saying that paraphrase that the most incomprehensible thing about the universe is that it's comprehensible. So I think the first thing is this whole foundation on which we're doing the experiment that says the math describes a understandable universe that clearly operates within certain prescribed laws and isn't just this random thing. To me, that's quite remarkable.
Yeah, there's a part of that, and especially what we're talking about here. It's not just like, well, it kind of generally agrees. There's a ridiculously high level of correspondence between the two. We're talking calculations out third, fourth, fifth, and more decimal places. It's not just a little bit close, it's incredibly close. And that's a phenomenal thing that I think as physicists we kind of get used to, but it's a really remarkable thing too.
Well, and I think as naturalists, the scientist gets used to it. The non-theist will say, if I can write an equation, then I've solved the problem, as if the equation even has anything more than, a descriptive power. An equation doesn't really have explanatory power as to where the universe came from or why it works that way. It's really a description. And yet I think even scientists overlook how remarkable this is, that we can write theories that agree with experiment to the fifth decimal place. And when we're off by, 3 standard deviations, we start to think maybe something is new going on.
So how else, you said that was one way that just there's this remarkable correspondence between our mathematical theories and the way the world actually works. What else comes into play there?
Well, I think the other is probably related. It's the fact that we believe that that the universe that we see is kind of a holistic thing, right? It's the cosmological arguments that says we must have dark matter. And the reason, and dark matter, therefore, has driven much of particle physics. This idea of supersymmetry, which is a theory that has been proposed in particle physics. There's lots of reasons why we think supersymmetry might be true, but it would answer the question of the dark matter. Again, you have this idea that if I see something in nature, there is an explanation for it. A rational, I would argue, even looks like intelligently designed explanation for it. And if we, and therefore we look for it. In fact, scientists are uncomfortable with things that are extremely finely tuned because it looks like, therefore there is a designer, but I would argue the whole universe looks finely tuned. And so the whole universe looks for a designer. So the fact to me that I am following the evidence, because there's evidence to follow, points to a probabilistic argument for some kind of deity.
Your statement there about the fine tuning and how that tends to trouble. One of the things that I have found, you're talking about dark matter, where the idea is, well, we've got this stuff out there. There ought to be some sort of particle, and so we measure its gravity, what kind of particle, and so there's this connection between the cosmos and what we do in our particle accelerators. But cosmologically, we know that there's this stuff out there called dark energy. And following the line of reasoning you've articulated, it's like, okay, we have these ideas of where the dark matter particles might be, and so we can go look for that. But this standard model is so effective at describing things. When you ask the question, where would the dark energy come in, it's at such an incredibly high scale, incredibly large energies, that the discrepancy between where we expect it to be and what we actually see is huge. And so this is one of those fine-tuning problems, because it doesn't look the way we would expect it. It's not natural, if you will. And so my understanding is that's even true of the Higgs mass as well, is that it's different than what we would naturally expect it to be.
Well,
and that's an interesting.
Yeah, there is an issue with the mass of the Higgs being very, very small. And there are people who would argue you can only get that if you subtract two large numbers within the theory.
Right.
That's not totally accepted by everyone, but I do think the Higgs boson mass itself is interesting, because it stands at a place where it makes the universe, if the Higgs mass, I can't remember, heavier or lighter, the universe is kind of unstable. And if it's the other way, it's very stable, but it's kind of in a metastable state. And so I don't know what that means for God or anything else. But it's an interesting fact about the universe. I mean, one thing about, studying the universe is, you said a few things. One is, you said, I can't remember what you're referring to, but it was something, that God isn't doing it supernaturally. I can't remember exactly what you were talking about just a few minutes ago. But when we find a phenomenon we can't explain, yeah, I know it's not because God did it. In scripture, God is constantly working through the laws of nature he created. And so when I find a phenomena that is unexplained, my expectation is that God created something within nature to explain it. And that when we find that, it's going to be remarkable, and that it's exactly what's needed for nature to work, but not remarkable in that it's God supernaturally doing something to make nature work, if that makes sense.
Yeah, no, I think that makes a lot of sense, because, and I wonder, I think there's a history to the way that people think about that. But, we've got these phenomena like the dark energy is much less in measure than what we expect it to be. Let's say that's true of the Higgs mass as well. There's just numerous examples where things appear very fine-tuned. And so the idea is there ought to be an explanation for why that appears fine-tuned, so that it isn't actually fine-tuned, if you will. And that, one of the paper that I was reading was talking about how to solve some of these fine-tunings. And there's typically been two options, and you alluded to one, that there's a new symmetry out there. There's physics we don't understand. So, like with the dark matter, there's this other stuff, there's these supersymmetric particles, and that will provide the explanation for the dark matter. Or, maybe there's some symmetry that can explain the dark energy in a more natural way, if you will. So there's kind of a new physics or a new symmetry out there that we haven't discovered. That's tends to be one class of explanations. Another class of explanations is kind of a statistical approach that, the multiverse tends to play very prominently these days in those sorts of explanations. Yeah, these things could be very different, and you're not going to get life, but the multiverse has all of these possibilities, and of necessity, we're in the location where you get the universe where we could live, the region of the universe. And so what I found, this particular article was talking about a third way of explaining those fine-tuning, or those those things that look fine-tuned, in that there are triggers for what's going on. So, it could be that as things are just changing and evolving, that when a certain parameter crosses a threshold, it produces a multiverse or universes that are habitable, if you will. And so it provides a natural way of explaining the fine-tuning. But I love the way you described that. It's like, it's not that I expect some supernatural explanation. You actually expect that, okay, God has orchestrated things so that it works the way it's supposed to.
Yeah, I often, one of the examples that I often talk about with fine tuning is the matter density of the universe, which, in the early universe was fine tuned to 1 part in 10 to the 60th. So this is, if there's too much matter, the universe collapses in on itself, and if there's not enough, then you can't form stars and galaxies. And it's fine-tuned to 1 part in 10 to the 60th, and we think we have an explanation for that. It's called cosmic inflation, and inflation kind of forces the matter density to be what it should be. But for cosmic inflation to work, it's got to turn on at just the right time and turn off at just the right time and have just the right magnitude. In other words, to me, if you have a mechanism that produces something that's finely tuned, you've just kicked the can down one notch. Where did the mechanism come from? The example I always give is when I dump gas into my lawnmower, it spills all over the place because the lawnmower hole that I'm trying to dump it in is finely tuned. But if I use a funnel, then I can dump it anywhere and get it right where it needs to be. Mm-hmm. But the funnel's finely tuned. The mechanism is finely tuned. And so to me, the holistic, remarkable universe we have, that if you change any little thing, it goes away. The fact that nature works is evidence of God. This is, to me, what Psalm 19 says, right? The heavens declare the glory of God, the skies proclaim the work of his hand. And if you ask, well, how do they do that? It's because the sun rises and it goes back to where it's supposed to, and everything works like remarkably. Right. And this is my fascination with nature. It works. And every time you discover something new, as you said, it's not what you expect, but you realize it's ultimately required to make the universe work.
Well, and I kind of wonder if the church may not have propagated some of this division or the wrong way of looking at it by saying, okay, we know the place, I'm going to give it I think it was well motivated. Well, if where God works supernaturally, science isn't going to be able to answer that. So those are the places where, okay, we can definitively say God's work. But, as I've thought about it and talked with theologians, I realize that God is at work in everything. There is no distinction between, the supernatural and the natural. And it's like, okay, God does the supernatural and the natural. We kind of have this dichotomy that is not really theologically a sound way of thinking about it. That, in scripture, God formed David in his mother's womb. Well, I can give a whole lot of scientific description of how that works. None of that negates the fact that God's at work there. And so as Christians, we may have contributed to this misunderstanding by saying, oh, God is only in the place where it's beyond our explanation. In reality, God, as you said, I expect to find an explanation for why these things work the way they do because of how God is created and who God is.
Yeah, in fact, there's so much to say about that. You wrote a great article about 3 golfers that I have quoted many times and I reproduced in my blog, because it's exactly to this point that we see God in nature just through the natural working, as well as through, hypernaturalism. We don't have to explain that, and as well as through supernatural. And this is where, to me, as a physicist studying nature, looking for other Higgs bosons is so compelling, because you are looking at a piece of art that the artist created, and you learn things about the artist, not by how he created and what he created. And so, the order I see and the creativity, who would have ever, come up with quantum mechanics? I give a whole talk on that, the creativity and the order and the design and the fact that it's understandable, it all points to a truly intelligent designer behind it all. And it's not because I can't explain it, it's because I can explain it.
Exactly. And that's what, as I was thinking about this third way, either the statistical explanation, the new physics explanation, or where this trigger generates the thing that is necessary. I mean, I can't tell you how many times I've looked at stuff where, I always wanted to make a Pinewood Derby, or where you roll them down the hill. And my way of doing this is I wanted to put a CO2 cartridge in it, because if you can give just a little bit of speed right at the start, you're just going to win every single time. Well, the problem is, how do you do that so that I can't touch the car, but it works at the right time every time? And so designing a mechanism where it naturally, as you set it down, it resets the trigger, generates it for that little bit of time. If I were to go accomplish that, somebody would look at that and say, wow, that trigger is incredibly well designed. And so if we find something that triggers the formation of livable universes as this amorphous stuff evolves and it's generally hostile to life, that would just be, wow, what a fascinating, incredibly well-designed mechanism, that it gives exactly what you need and eliminates all the stuff that is kind of unuseful. I mean, it's used as a way to get rid of the fine tuning, but it points even more to design in my assessment.
Yeah, again, Jeff, I've learned a lot from you. Your little book on the multiverse, which Who's Afraid of the Multiverse, talks about this, right? If we discover multiverse, ultimately, I'm convinced it's going to enhance the understanding of design of this universe more than it detracts to make it a statistical argument, because that's been the history of science as we've done it. Everything we find, even the things that first appear unremarkable, turn out to be quite remarkable.
Well, thanks, Mike. I really appreciate our time today. It's been fun discussing with you. It really is the case that when we look at our universe, the more we learn, the more we have reasons to believe that a God exists. Again, I would encourage you to go check out our website, reasons.org. Lots of articles, lots of information you can consume there. Check us out on social media at RTB_official. Go to our YouTube page and like us and follow us and subscribe to us so that you can get more reasons to believe.